Sorry.
I always forget. That's okay. I can color it. Yeah, there we go. Okay, so last time we had just started talking about tensor network models of holography, with the motivation being to try to find something that's in between the 3Q-tret model, which is kind of trivial, and n equals 4, which is kind of complicated. And so the idea was to use these tensor networks, which I briefly introduced yesterday. So in the 3Q-tret model, remember we had I said this backwards. So in the 3Q-tret model, we had one logical qubit and Q-tret, and 3 physical Q-trets. And so the idea here is that we want to get some set of models where we can take both the number of boundary degrees of freedom and the number of bulk degrees of freedom to be large. So in order to give you a code with k logical qubits and n physical qubits, and now I will be doing qubits, we saw that I need to give you this tensor, which just gives you the wave function of each. You have a complete basis of the code subspace here, and I just have to give you, for each basis element, its wave function in terms of the physical degrees of freedom. And so that defines some big tensor with n plus k indices, each of which runs over from 0 to 1. So then the idea was that since this is a tensor with a lot of indices, one nice way of breaking it into more manageable pieces is to represent it by taking a bunch of tensors with a small number of indices and then contracting some of the subset of the indices together in a geometric pattern. And then the remaining indices that we don't contract become the indices of this tensor. And so I drew some simple example of that on the board. So here there are 3 4-index component tensors, and then I do 3 contractions in this triangular pattern to leave me with however many indices. This is left over 6, I guess. Of which I decided that these 4 are the physical qubits and these 2 are the logical qubits. Okay. Now, in order to actually tell you what is the T, I have to both tell you the network and I have to tell you what are the component tensors that I'm going to use. Okay. So now let me say that. So my component tensors are going to be what are called perfect tensors. So a perfect tensor is a tensor with an even number of indices, each of which has the same range. So for us, it's going to be qubits. So it'll be some tensor with an even number of 0, 1 indices, which has a very special property that any balanced bipartition is unitary. Okay, so what does that mean? Well, so say here's some perfect tensor sitting here, and let's say I split its input and its output into pairs, into some subsets. So the idea is that this is half of the indices and that's half the indices. So that's why it needs to have an even number of indices. Okay. So now, first of all, since this is an example of a balanced bipartition, this has to be unitary as a map from these qubits to those qubits. Okay. But now the claim is that, well, I could take the same tensor, but then I could do something like this. Okay, and now I could say this is the input and that's the output, and still it would be unitary. And in fact, that'll be true for however you move it. You move the indices back and forth between the input and the output. So it's not obvious that perfect tensors exist, right? There's a very strong constraint on the tensor. And in fact, if we fix n and k to be something specific, and we say specifically we're talking about qubits or qtrits or something like that, there will not be any perfect tensors. Okay, so it's only for special values of n and k, and for d, which means qubits, qtrits, etc. There are only specific values for which they exist, but there are some for which they do exist. And in fact, we've already met an example. So let me tell you what it is. So our first perfect tensor that we can discuss is a perfect tensor with 4 indices. And it's just the encoding map of the 3 qubit code that we've already met. So the unitary is basically, so remember we had this U12, U23, and U13 for the 3 qubit code. And actually those are just these different ways of crossing the indices in this tensor. And so the fact that there was this split into a unitary, whichever way we did it, is exactly saying that this is a perfect tensor.
So one-to-one map in perfect tensor, then error-corrected code?
Yeah, that's right. Well, there's, I guess, an injective map. So every perfect tensor gives you an error-correcting code. Not all error-correcting codes come from perfect tensors. Yeah. But you can't have one of these without having an error-correcting code. And the simple error-correcting codes people talk about are basically always associated with perfect tensors. They're called stabilizer codes. Okay, so this comes from, this is a 4-index perfect tensor from the 3 qubit code. Now it's not actually, this is just, it'll be annoying for a sec, but I'm about to do the slides, so.
Oh, you are?
Just leave it, because I'm about to do the slides. Yeah, well, I'll turn it off after I do the slides, but this is okay, we can tolerate it for 2 minutes. Okay, so this is an example of a perfect tensor. The perfect tensor I'm going to use to make a holographic model is not this one. It's a different one, which is based on a different code, which is called the 5 qubit code. So this is the 3 qubit code. So the 5 qubit code, you have 5 physical qubits and 1 logical qubit. And so I won't construct for you this tensor. I'll just tell you that it exists. You can construct it using similar means to how this one was constructed. Although I didn't explain it to you there. I just wrote it down for you. But here it's a little bit tedious to just write it down for you. But this is a code which predicts this 1 logical qubit against the erasure of any 2 of the 5 qubits. So since you have more physical degrees of freedom, you have better protection. You can lose 2 instead of just losing 1. And you can still recover the logical information. Okay.
That's the unique 6 qubit.
It's unique up to trivial things like unitaries on the, yeah. That's right. Okay, so how many indices does this have as a perfect tensor? 6, right? So it's 5 plus 1. So that means this is a tensor where any split of it into 3 indices and 3 indices is going to be unitary. Okay. Now I need one more property of perfect tensors, and then I can tell you how the holographic model works. So this is kind of trivial, but I just want to say it explicitly so it doesn't surprise you later. So there's a pushing operation on perfect tensors. So say that T here is a perfect tensor, and O is an operator. And so this is some split. This is half of the indices, and this is half of the indices. It doesn't matter which half I pick. And then these half of the indices are contracted with some operator that, just any operator that acts on those, in this case, 3 indices. Okay, then the claim is that there exists another operator, O prime, such that this is equal to that. So I can push this operator through the tensor at the cost of changing the operator. And there's nothing mysterious about this. It's just the obvious thing. So this O prime is you put in T dagger to cancel this, and then you put in O, and then you put in T, and then you use that T as unitary however you split things. Okay, so it's the obvious thing. So this is called pushing. I can push this operator through the tensor to turn it into another operator that's contracted with the other 3 indices. All right. So now I'm going to switch to the slides. So that tells you the components. To tell you the network is hard to do drawing things on the board. So I need to use the computer. Someone want to press 8, 9, 10? Okay, and then I think I know how to do this, but let me just check. All right. I practiced. Okay, so the idea is that I'm going to start with the tiling of the hyperbolic disk by pentagons. And so this is kind of going to be a model of AdS3 CFT2. So this is a time slice of AdS3. So you see here the pentagons, and you can see it's kind of fun to play with the software. Yeah, we could just kind of sit around and watch this for the rest of the lecture. But I think
what software is this?
It's called Kaleidotile. With some you can get it for free online. You can do any symmetry group you want. So there are these like triangle groups or whatever that label lattices on. Okay, anyways. So I take this tessellation, and now the idea is that I'm going to stick a tensor in the center of each of these pentagons. So using another advanced software feature, I can show you how to do that. There. So good. So each of these black dots is going to be one of my 6-index perfect tensors. Now you might say, wait a minute, that looks like 5 indices. And that's true, but remember in the tensor network, we want some of the indices to not be contracted. So in each of these dots, there will be 5 indices who are contracted with the neighbors, and then there will be another index sticking out, and that will be my J index, which labels degrees of freedom in the bulk. So this bulk theory has a qubit at each of these black dots. So now we have kind of a volume's worth of effective field theory degrees of freedom in the bulk. Now, you might ask, what about the boundary degrees of freedom? So that's a little bit harder to show here. So now I'll show you how this picture looks when my collaborators draw it. So it's the same network. Now the red dots are the logical J indices coming out of the bulk. But the key thing is now we have to put in a cutoff at large radius. And then the idea is that at the cutoff surface, then everybody who's going out, you call those the physical qubits. So here the physical qubits are the white dots. So these white dots are the degrees of freedom in the boundary CFT regularized with a UV cutoff, right? And then as we take the IR limit in the bulk, that's taking the continuum limit in the boundary theory. So you see now we can arrange for both n and k to grow in this limit, in this sort of pseudo continuum limit. It's not really a continuum limit because, for example, it doesn't have continuous rotation symmetry, even in the limit, because, for example, this tensor in the center, right, it only has a Z5 rotational symmetry. So it's not quite a continuum field theory in the usual sense, but it's some kind of continuum theory. And it preserves some discrete subgroup of the conformal symmetry, basically the subgroup that preserves this lattice. Okay, so that's our code. So now let's see to what extent we can reproduce the properties of holography. Maybe I'll try to use the laser pointer. Yeah. Okay. So the first point now is we can do this business of reconstructing bulk operators on a subregion of the boundary. So let's see. So for example, so here's the dangling index. So now I switch back to my picture, sorry. So now the red dots again are the tensors, and the black lines, I guess I did it the other way before, but okay, anyways. So say this blue box here is like a field operator at this point in the bulk. And I want to know how can I represent that in the boundary. Well, so I can use this pushing operation I just described. So I can say this is an operator that goes on this index of the perfect tensor, and then I can say I feed in the identity on these 2 indices, and then I can push it to some operator which has support only on these 3 indices. And then I can keep going. Like I can push this one, I can say it's the identity on here plus the dangling one, so I can push it onto these 3. And then I can keep pushing, and by the time I'm done, I get some operator in the boundary of CFT with support on this subregion. Okay, and so that's the kind of the AdS Rindler reconstruction.
There are other ways of pushing it.
That's correct. And I'm going to comment on that in a sec. So yeah, and let me comment on that now, right? So as David said, right, this was not a unique choice. For example, this index I could have sent down here, and then I could have gone down here, and then I would have gotten some representation like this, right? Or I could have sent to these 3, and then I would have got some representation like that, and that's...
More confusing with indices on the tensor.
What?
The pushing indices are adjacent.
Good. So I'm going to comment on that later. Yeah, that's right. So I can even not choose them to be adjacent, and so I can send 2 of them this way, and I can send 1 of them that way. And we'll see soon that actually has an analog in AdS CFT. So yeah, here it looks a bit surprising, but in the end, it's a true feature of the correspondence. So let me also say that so I could, for example, I instead could have considered a bulk operator over here, and then you can see when I push it, it just goes onto a smaller region of the boundary. And so that's this relationship we saw before between the radial direction and the degree of protection. So this operator I can represent smaller. And so you see it's clearly if I move them closer and closer to the boundary, I need fewer and fewer boundary qubits to represent the operator.
There are really exponentially many ways of doing
Yeah, absolutely, yes. Yeah. That's right, and that's because it's a sort of a good code. It's a, this information is very well protected. So even if you just delete some sort of fractal pattern on the boundary here, you have a choice how you push things, so you can try to avoid it. That's right. And that actually means this is a pretty good code. So codes are sort of measured by what fraction of the boundary qubits you need to recover, and kind of good codes are ones where it's kind of a finite fraction. Where you can correct for the loss of a finite fraction is a good code, and that's true here. And that's part of why I think these codes have been interesting also for the quantum information people, is because it's non-trivial to come up with codes that protect against finite fraction errors. For example, the toric code does not, right? So the toric code, people talk about it all the time. That is worse code than this from the point of view of the rate.
In some sense, you could do this with 2 to the 2n tens of perfect tensors and get a finer, better code.
Yeah, that's right. So there's the IR. So of course, in practice, you'll always have an IR cutoff, right? But then making the IR cutoff bigger and bigger is kind of making the code better and better. But as usual, there's a trade-off because the engineering.
Also, you have freedom of the number of legs.
Oh yeah. So you can also try to increase the number of legs on the perfect tensors. Then the network kind of so then the exponential growth is faster and faster, but then you also pay the price of having a bigger tensor at each point. So yeah, I don't want to say this is optimal. This is just the first one that we thought of. They're very actually. In fact, if you're really trying to optimize it from a coding point of view, you do a little bit better by kind of alternating pentagons and hexagons. And then in the hexagons, you don't have a dangling index. You just shoot out all 6 indices, and that actually gives you a higher rate. So for coding applications, probably you would do things like that. But here I'm just trying to come up with the simplest model, so I'm not going to do that. Yeah.
You said you have choices for how to push the indices. So what determines the choice?
Nothing. It's up to you.
What you want to
You do whatever you want.
Up to who? I mean,
Up to you or me or whoever's doing it.
every person has their own vote. I mean,
No. It's the same operator. So within the code subspace, however you push it, it's the same operator. So if we just look at its matrix elements on the code subspace, they're all exactly the same. And that's what we found in the bulk too, right? It was just different Bogolubov representations of the same operator. So it's like choosing a basis in linear algebra. You can pick whatever basis you want.
but if a particle got erased on the boundary, would the position change?
Well, so if a particle if you didn't have access over to the region over here, it would be kind of stupid for you to push the operator over here. You could, and then you just wouldn't be able to use that operator. But if you happen to know that you don't have access to this, then if you're smart, you'll probably push it this way. Okay. Chenty, what's up? The signature of what? Sorry, you mean Lorentzian versus Euclidean? Well, this is Lorentzian because I'm talking. Well, I mean, this is a time slice, so you can't really tell. I'm talking about the Hilbert space on a fixed time slice, so you can't really tell. There was one other question. Yeah.
You said the AdS symmetries are broken into this discrete subgroup of letters.
Yeah.
Is there a way to see that manifest in this boundary?
Well, it's kind of manifest from the construction because the network manifestly preserves some subgroup. It's just the name of the subgroup is the subgroup that preserves this lattice, so it's a bit circular, but it's a fairly big subgroup. You can ask whether the tensors do, but in fact they do because I didn't tell you what the code is, but these tensors have cyclic permutation symmetry around the 5 indices, and so that's good enough because the subgroup you get isn't going to be flipping orientations of things anyway. So.
Because the network and the tensors feel to me like they're bulk descriptions.
Yeah.
So I was asking about the boundary.
Well, it's kind of defined by taking this and then taking the cutoff. So you can worry, as usual in AdS CFT, that once you take the cutoff, you're kind of picking a conformal frame on the boundary, and so that'll transform in some non-trivial way. But as long as you're careful about that, then that's all it will do. Yeah. Invariant under what?
I mean, because you said you have your choice to push your...
Yeah, but how things act in the code subspace is going to be the same. So The whole point of this is that you have this redundancy of how you represent the operator, but it's the same operator logically.
Yeah, but what is the range?
Yeah, it's how it acts within the code subspace. So all these operators differ by how they act on the orthogonal complement of the subspace. But they all act the same on the subspace. So I can use whichever one I want as long as I know that the system is in one of the code states.
So for example, the algorithm operator
Yeah, the algebra is all the same. Yeah. And it's kind of, some of it is kind of funny, right? Because, for example, if, say I take this operator here and this operator there in the bulk, they commute, right? No matter what operator I put here and what operator put there, they're on different sites that they commute. But now just push this one here and push this one here, and then ask, do they commute in the boundary? Well, apparently the answer is yes, but if you just stare at it, good luck, right? Some big non-local mess, commutator of that with some other big non-local mess with similar, with this overlapping support, but miraculously they commute on the code subspace. Yeah, okay. So if you like it, some formula, you can think of this as some formula for saying here's some big non-local mess in the quantum field theory that actually it's 0. Or more carefully, it's 0 to very good accuracy. Yeah. Okay. All right. So now remember last time I talked about this. We had these theorems about encoding circuits. So let me show you how that works here. So remember I said that. So we talked about this idea where everything in this subregion should be representable here, and everything in this subregion should be representable here. And I said, but didn't show, that a generalization of the theorem that I proved last time will tell you that the encoding map has to have this structure. Okay? And so then you can see this structure geometrically in the network here. So this tensor network, so basically this chi state that you feed in is here it's a set of EPR pairs which are along this surface here. And then you can show that everything to the left of this surface can be pushed here, everything to the right of this surface can be pushed here. And then so this state chi is exactly these bell pairs along the surface, which we're soon going to see is going to be the HRT surface. And so this UR is the chunk of the network sitting here, where you view the input as being all the red dots plus all of the lines coming out of the HRT surface. And the UR bar is the network here, where the input, again, is all the red dots over here plus all the lines coming out of the HRT surface this way. Okay, and so this kind of geometrizes this quantum circuit picture. Okay. Now let me say one other thing, so you can ask about the states that aren't in the code subspace. So I told you that they're black holes. So here we can see how it works. So now let's take the whole network, and then let's remove the tensor in the center. So previously there was one input here, but now there are 5. And since all the other inputs are still there, it means that this is now describing a bigger Hilbert space than we were describing before. And there's a 2-dimensional subspace of it, which I obtained by just putting the tensor back here. But in the other states, it's not. And so again, now I want to claim that that corresponds to a black hole sort of 1 AdS radius sitting here. And indeed, you can see that the rest of the bulk is fine. So, I put operator here, I put operator here, or here. I can push it this way, or I can push it that way, and it all works the same. But now there's just this obstruction in the middle. And you can see that you can compute, if you like, the Bekenstein-Hawking entropy of this by counting how many states you can feed into these green dots. So these are like the sort of horizon degrees of freedom of the black hole. And similarly now, we can get an even bigger subspace by, say, I remove all these blue ones. Okay, and now I get a bigger black hole, which has even more microstates. And there's still some region of the bulk which is left over, but now it's smaller. And if I keep going, I keep removing tensors. Well, eventually I'll have removed all the tensors. And then the map will just be the identity sitting out here at the horizon. And so that shows you that, indeed, you can if you think about the whole Hilbert space of the boundary theory, it has this hierarchical structure in terms of bigger and bigger black holes. But as you go to those, you lose more and more of the bulk. And so, again, I claim this is really a model of the whole correspondence, not just the low-energy states. And you can check that, the entropy goes like the area, although that is a little bit trivial because in hyperbolic space, the entropy and the area are the same. But more carefully, you can check the power of n and see that it works. To do that, you have to allow the number of indices on these things to grow, and then you can see that things scale in the right way. Yeah. Okay. Yes.
So you don't have microstates behind the horizon?
Well, I'm not sure what you mean. The black hole has microstates. So I would say, probably that if you know the microstate, then I think you should know what's going on in the interior. But that's I don't know because we don't understand the black hole interior, and there are people who think otherwise. So, but
Different points.
uh,
What are the shared points?
what?
For different coins,
Yeah.
what are the shared?
What do you mean shared quantity?
These 2 points, which point are the same?
Nothing. These are all different inputs. So now I'm viewing these green dots as logical inputs. So this is an independent degree of freedom from that, from that, from that, from that. So so the black hole has the entropy, which is associated to the state you feed into the green dots.
You're saying that the bigger inputs would be replaced one.
Yeah, that's right. Yeah, and so the one is the one where the black hole is not there, but then in the rest, the black hole is there, and these are its microstates. Yeah, yeah, Eric.
So how could this object evaporate?
Well, big AdS black holes don't evaporate.
A small one?
Well, a small one is I don't really know how to talk about a small one here, right? I mean, I've kind of discretized the world at the AdS scale. So, unfortunately, there seems to be a rather general property of AdS CFT that whenever you have a solvable example, like these guys or SYK or higher spin, vector theories, it's always non-local at the AdS scale in the bulk. I don't know. That's life. Yeah.
So you said that the Patchwork described HRT surface, which is intrinsically time dependent. You don't have any way to describe dynamics in this setting, for example.
Yeah, so the dynamics are here only. Yeah, so the dynamics are here only in some rather trivial sense. I picked these particular subspaces to interpret in a certain way. And roughly speaking, what I would like to say is that this subspace is sort of the set of states of sufficiently low energy. Maybe states whose energy is less than n squared or something like that. And then now this one already, now I'm allowing states of slightly higher energy. And if I allow the bigger ones, the energy gets bigger. But that's kind of the extent to which I can talk about the Hamiltonian in this model. Like, I don't actually have a formula for the Hamiltonian. So, this is kind of a kinematic picture. I mean, it's because somehow I'm really trying to understand the duality of fixed time. Yeah. Now, of course, in the end, it would be nice to know more about the Hamiltonian or somehow pick in a nice way a boundary Hamiltonian that has these kinds of states as the subspace. But that has not been done. Yeah. Well, I could certainly put in more than one black hole. Like, I could remove this tensor and also this tensor. But the boundary is connected. So anything which is connected to the boundary is all going to be connected. Are you asking about could I have a closed universe floating over here? I don't know. That's a question. In AdS CFT in general, I think we don't know the answer to that question. I mean, in some sense, answer's got to be no, because you could put it whatever you want in that closed universe. It has zero energy. But I don't know. That starts getting into philosophy. I don't. Yeah. Okay. Last question. Yeah.
So is there some way to see that the curvature should be different than in the black hole?
Well, I'm not sure what you mean. I mean, the space-time is gone in the middle now, so I guess, yes, the curvature is different, because before it was something and now it's nothing.
Well, I mean, the curvature near the black hole.
Yeah, that's kind of this back reaction. I mean, somehow the funny thing about AdS is that gravitational back reaction kind of falls off exponentially because of the negative curvature. So in this model, gravitational back reaction is just purely this question of is there a black hole there or is there not? It's kind of a very primitive sense of gravitational back reaction. Yeah. What can I say? I said it. I said I would be somewhere in between the real thing and the 3Q-trit code, right? But I think it's kind of to me, this is kind of like the skeleton of holography, right? It's kind of, it's not the whole story, but it's kind of part of the infrastructure. It's enough to kind of see this emergent radial direction, which maybe people would say is or at least one of the most mysterious features. Yeah. But here it's kind of obvious. All right, fine. Really the last one this time.
I was just wondering whether you could see some sort of gravitational back reaction. Try, say, reconstruct an operator on one side of the black hole in terms of pushing it across the black hole on the opposite side. You run into these black holes that you just free up.
Yeah, that's right. So you can certainly see that the regions that you can reconstruct get smaller, and you can try to interpret that in terms of this HRT, how the HRT surface gets deformed in the neighborhood of the black hole. Yeah, morally that's kind of correct. I'm not sure I can say it more precisely than that. Yeah. Okay, so that's all I was going to do with the slides. And that was going to be the end of yesterday's lecture. So yeah, let me now figure out how to turn this on. I'll put up the screen. Oh, come on. Okay, now off. Well, I don't want that logo to show up again in a few minutes. Pressing off. Well, okay, I pressed off 5 times. Well, it's off right now, but then it came back last night. Okay, let's wait. Don't solve a problem until we have it. Very good. Okay. All right, so on to lecture 3, where we talk about the Kannagi formula. So, yeah, I guess maybe I'm the first person to mention the Kannagi formula in the lecture. I guess I wasn't at all the lectures. So let me just advertise that. I mean, all this stuff, I think, in some sense, came out of the Kannagi formula. It's a funny thing because, in string theory, the previous, whatever, people like Brian Greene call them revolutions, sort of came quickly, right? Where there was something, and then within a few months, everyone was working on it. For me, the Kannagi formula is comparable to something like the duality revolution or anomaly cancellation, but somehow it took a bit longer for people to figure it out. But anyways, it's here now, and it's kind of lying at the root of many of the things you hear about. Okay, so that's some advertisement. Okay, so what is it? Okay, so I have to start with some geometry just to set the terms on the table before I can say what the formula is. So the idea is that we're given a spatial region R in the boundary, an asymptotic boundary. And given that spatial region, we can define the HRT surface gamma R, which is defined so it's defined by saying it has to obey some criteria. So the first criterion that it has to obey is that so it's a codimension 2. So in AdS 3 it's a line. In AdS 4 it's a 2-dimensional surface. Okay, so it has to obey some criteria. So the first criteria is that the boundary of the surface has to be equal to the boundary of the subregion R on the boundary. So this is sometimes described by saying that it's anchored to the boundary region R. Among the set of surfaces obeying this condition, the area of gamma R has to be extremal. Okay, so in AdS 3, that would be saying that it has to be a geodesic. Well, in higher, it's codimension 2. So if we're in AdS 4, then it's a surface. So it's not a geodesic. Yeah. Then there needs to exist a codimension 1 surface, HR, which is space-like, such that the boundary of HR is equal to the union of gamma R with R. So this is sometimes described as saying that gamma R has to be homologous to R. And I'm going to draw a picture in a sec, but I want to write all the definitions first. And then finally, it has to be that there does not exist some gamma R prime of smaller area obeying the above. Okay. So let me draw a picture.
Does that just mean the area is not just extremal, but is a minimal?
It's minimal. It's not. No. The problem is in general relativity, you can always make the area of something small by taking it just to be null, by making it wiggly. So you can't say that the area is minimal. The area is minimal if you have a surface of time reflection symmetry and you require the surface to be in that within that time slice, then you can say it's minimal. But that's not covariant. So what I'm giving is I'm doing some alternative history here to simplify the answer. So as with many things, it's discovered in some stupid way and not the most general, and then people added more things and the terminology got all confused. But my philosophy in life in general is I never respect historical terminology unless it's actually good. Okay, and that's going to be what happens here also. You should always use the best terminology. Don't be saddled by the misunderstandings of previous generations. Okay, so this is a covariant definition. HRT here stands for Hubei, Ragamani, and Kannagi, who are the people who figured out how to covariantize this earlier definition, which you should forget about. Okay, so let me draw a picture. So I'll draw it in AdS3. So say here's some time slice. And let's take R, our subregion, to just be some interval here. Okay. So then gamma R, so what this means is that it's codimension 2, so that means here it's a line. This says that the endpoints of the line have to be the endpoints of R. And this says it has to be a geodesic, so it'll be something like this. Okay. Now this HR will be this region here, or we can take it to be that region there. Okay. This HR is sometimes called a homology hypersurface. I think it's a good name. And then this condition is saying that there can't be some other gamma R floating around somewhere else which has smaller area. Okay. Now there are a number of annoying questions about these surfaces having to do with existence and uniqueness. I'm going to ignore all such questions. So I'll just assume that there is one surface that obeys this condition. If you want to worry about those things, come talk to me later. I have worried about it. So far, nothing good has come out of worrying about it. But maybe that'll change. Okay. Now I want to. So that's the first geometric definition. Is this? Well, I guess I made two definitions. I defined gamma R and I defined HR. I didn't label it here. Let me label it. This is gamma R. Okay. Now there's another very important definition now which I want to make, which is the entanglement wedge. W of R, let me call it W sub R, which is defined as the domain of dependence of HR. So let me remind you that in general relativity, or in any Lorentzian manifold, the domain of dependence is defined as the set of points where every inextendable causal curve through that point must also intersect this surface HR. So if you think about it, if you think about specifying initial data on HR, D of H of R is kind of the region where the solution of the wave equation is uniquely determined, given the initial data on D of H of R. And so that looks like something like this. It actually looks pretty similar to the wedges that we were drawing before. Because anything that I can get to, say, with a null curve from here, I could put some initial data here that we need to know about.
Also the past.
Yeah, and the same. So this is going in the past also. Yeah, so it's this wedge. Yeah. Okay. So now, in fact, so this looks like the causal wedge that we defined before. It looks somewhat like this C of R that we defined before. But in general, they're not equal. So the C of R we defined by we took the boundary domain of dependence of R, and then we took the intersection in the bulk of its future and its past. Here we took this homology hypersurface, and then we took its domain of dependence in the bulk. The two are the same if you're in empty AdS and R is a ball-shaped region. And since that's what we did with the AdS-Rindler reconstruction, in that case they're the same. Okay, which is why I didn't need to talk about this before. But in general, they're not the same. But in general, there's a nice result, which is that CR is always contained in WR. WR is bigger. This uses the null energy condition, otherwise it wouldn't be true.
You're just saying that the matter in the bulk, has positive.
What kind of positive null energy, if you like? Yeah. I mean, so maybe I'll just say, I can say for anyone who knows some GR, I can say why this is true, but it won't help you if you don't already know what these words mean. So the difference between the two is that the causal wedge is defined as a kind of as a horizon. It's kind of defined by what's accessible from the boundary. And so it means it's defined by a null congruence which is fired from the boundary. This thing is the domain of dependence of HR, so it's defined by a null congruence which is fired from the extremal surface. So they're fired in different directions. And so they'll coincide if there's no matter that falls through the wedge, but otherwise they won't coincide. And what the null curvature condition tells you is that if there's matter that falls through here, then this one focuses. And so because it focuses, then it kind of gets to the boundary faster than the one where we fired going the other way. Okay. So you can go read Edward's PITP lectures if you want a place to learn such words.
So if they sometimes coincide, why do you have a proper subset?
Well, okay, yeah, this is a debate I have been having with my co-author. So, yeah, this is a notational thing. So I might have in the past written this, but Netta convinced me that it's better to write this. What can I say? I mean, if you say a subset, that includes the possibility of it being not being a proper subset. If you look at the definition of subset, and it gets kind of annoying to keep track of this. Okay, anyway, so I'm just not going to write that. I was converted. I forget all the arguments now, but anyway, she was right in the end, so I listened. Okay, so since the only example we discussed so far, they're the same, let's give some examples where they're different, just so we can see that they're different. Okay, and the first was actually hinted at by David in his question earlier. So the first example where they're different, maybe I'll draw it here. Is still you consider vacuum AdS3, but now I consider a region which is actually a union of two intervals. I'm going to put this here. Okay. So what would the causal wedge of this look like? Well, since this is a ball-shaped region, we know that the causal wedge. Let's see, is there colored chalk? There's too much trouble. Okay. So the causal wedge will be this shaded region here. Okay. And the union of these two geodesics is something that obeys conditions 1, 2, and 3. But does it obey condition 4? No, right? Not if this region is big enough, because there are these other geodesics here that I can draw. And if I make these intervals bigger, sooner or later this one is going to be shorter. And that means that so the causal wedge is the region I drew with the hashes, but then in the entanglement wedge, there's this additional region in the center here, which is included. And so, in particular, that's kind of what we saw in the tensor network, because we saw we could do this thing where we pushed sort of two of the indices this way and the third one up here, and that was taking advantage of this. So the tensor networks somehow know that, at least in that case, things that are in the entanglement wedge can still be represented in the boundary subregion R. And we're going to see at the end of the lecture that that's a general result. Okay, so that's one example. Now, there's another example which I really like. So this is based on some solution that Douglas constructed. So if you start with AdS Schwarzschild geometry in the thermofield double state, then again, if you look at well, maybe I'll draw that up here just for now and then erase it. So if you start in the Schwarzschild geometry and you ask, so now you take your subregion to be just this whole boundary CFT, this whole boundary sphere. So the whole boundary is the disjoint union of two spheres. I can take my R to just be one of the spheres. And then the causal wedge will look like this, and actually so will the entanglement wedge. And the two causal wedges will just be kissing in the center there. Okay. But Douglas has this nice paper with Steve where they show that if you kind of throw in matter in the right way, you can extend the length of the wormhole and make it look like this. And if you look at how the geometry is constructed, what you find is that, well, if you think about, let's first do the causal wedge of this boundary. Well, the causal wedge, by definition, can never go behind a horizon. because every point in the causal wedge has to be in both the future and the past of the boundary. Okay, and so anything like that is not going to be in a horizon. So the causal wedge will be like that. But if you ask where's the HRT surface of this whole boundary, actually it's sitting over here in the center. Okay, and so then if you fire the null congruence, sorry, I'm saying those words. If you look at the domain of dependence, so the homology hypersurface will be something like that. And if you look at its domain of dependence, it'll be something like that. And so then you get this whole extra region behind the horizon, which is in the entanglement wedge and not in the causal wedge. And that's kind of the most important thing about entanglement wedges is there's nothing to stop them from going behind horizons. And remember, that's what the thing we started with. We want to understand what's behind the horizons. So the causal wedge is kind of unfortunate from the point of view of trying to understand what's going on behind the horizon. Okay.
Is there a tensor network picture of this?
Of this longer wormholes? Yeah, I think so. Yeah, I'm not sure it's completely... Yeah, the short answer is yeah, I think you can do it. Basically, you kind of remove two of the tensors and then you kind of sew them together. So the naive thing to do is you'd make two of those black holes I drew and then you sew them together right on their microstates. But that's this picture. That's the thermofield double. But then you can sew them together by kind of gluing in some tensor there where it gets even smaller as it goes in, and then I think it'll be like that. But I'm not sure if it's actually been worked out in detail. Well, actually, sorry. In the examples where you instead of doing perfect tensors, you do random tensors, then it definitely works. Yeah, I'm not sure it's been shown for the perfect tensors. Yeah, I should have mentioned that. I meant to mention that and I forgot. So there's an improved version where instead of perfect tensors, you do random tensors, and then you can take the range of the indices to be large, and you can see this how this sort of scaling of the entropy goes with the Planck scale, if you like. Okay. Well, so each tensor. Yeah, you average. Yeah. Each tensor you average independently. Independently, yes. Yeah. We actually, when we were writing our paper, we tried to do it, but we were dumb, and we tried to do the averaging with each point being this. We tried to have them all be the same in average, and that doesn't work. But if you average them all independently, that works. Yeah. Okay. Yeah, and there's some paper with many authors from Stanford explaining that. Okay. So these are all just definitions. So now let's say what is the Ryu-Takanagi formula. And again, what I write will not be the Ryu-Takanagi formula as it appeared in the paper of Ryu and Takanagi. It'll be the current version of the Ryu-Takanagi formula. So what it says is that if we take some state in the CFT and we compute, we reduce to the subregion R, compute the reduced state on the subregion R, and then we compute its von Neumann entropy, then there's a bulk formula for that. So that's the exciting thing. There's a bulk formula for von Neumann entropy. Okay. And what the formula says is that we compute the expectation value of some operator that I'll call LR, and I'll say what it is in a sec, plus the entropy in the bulk of, so let me try to put tildes here to be careful. So in the bulk, we have this rho tilde. We compute in the bulk, we have a subregion here, this HR. So we can compute in the bulk, the von Neumann entropy on this subregion HR. Okay, that's what this is. Now, I have to tell you what this is. This LR is some operator, which is the area of gamma R over 4G, plus corrections, which are related to higher derivative terms in the effective action, which Shidong is very good at computing. But I'm not going to say anything more about the ... Okay. So this is the kind of modern version of the Ryu-Takanagi formula. In this form, it was first written down by Faulkner, Lukowitz, and Malacena, although even not quite, because they kind of still use the time reflection symmetry. So I'm not sure. Actually, this version, it kind of follows from some combination of things in various papers, but I'm not sure if there's one paper that derives everything here in the Lorentzian setting. But anyways, this is the formula. Yeah, normalized. Yes. Yeah. The trace of this is 1. A trace of that is 1. Yeah.
Can you generalize it also to spaces which are not AdS?
Well,
the paper by Klebanov and Causal, they claim that for non-conformal back ones, you can also have a similar RT
Yeah, I think that the derivation of Lukowitz and Maldacena should work also if there's some RG flow. Yeah, I haven't thought about it too much myself because I tend to not like turning on sources in the boundary theory. But yeah, but I think the same argument should work. Yeah. Yeah, and probably it's still the area. I don't see any reason why it wouldn't be the area. Okay. So this formula has, yeah, and then there's also in the formula, I should put here like a plus order G. So this is the formula that's true through order G to the 0. Yeah, higher orders in G, there's also a formula. It's called the Engelhardt-Wall formula. I'm not going to say anything more about it in this talk because basically I'm trying to reproduce for you sort of quantum field theory in the curved space. So I'm kind of working through order G to the 0. It's an interesting question how these ideas extend to higher orders in G. There's some things are known, but not everything. Okay. So that's the formula. It's been checked many times. It seems to be true. But there are a couple of funny things that I just want to comment about. Oh, sorry, a question, Shai? Yeah?
Is there any way to check the formula?
Yeah. I mean, there are examples where you can check it. In n equals 4, it's kind of hard, but with 2D CFT, there are a lot of checks you can do because 2D CFT is so powerful. So, for example, like in the like in the D1, D5 system, right, where it's AdS 3 times S 3 times T4, right? So that's the dual is some 2D CFT that we don't understand very well, but anyways, it's a 2D CFT, and so you can use the tricks of 2D CFT and check that it's true. Yeah, actually, one of the ways of doing this, I'll mention since Sasha is here, involves using semi-classical conformal blocks. So there's certain limits where the semi-classical conformal blocks can be used to check this formula, and it works. So that's for sort of arbitrary regions in AdS3 CFT2. So there's some papers by Tom Hartman and Tom Faulkner that do that. Okay. All right. So let me just now make a few sort of comments that maybe some of them occurred to you already. So the first thing you might wonder is like, what are the states where this is supposed to be true, right? So I said you take the CFT state and you look at the partial trace onto R, but I mean probably it's not true for all CFT states, or at least not obviously that it's true, And in fact, people usually, in the literature, sort of say pre-2015, they would just say, no, you're only allowed to work in states where the metric is in a coherent state, and there's, there's no superpositions of geometries, no black holes, nothing complicated. No black hole microstates, nothing like that. Okay, but is that the end of the story? Does it work in black holes? Does it work in superpositions of geometries? That's something you can wonder about, right? What is the regime of validity of this? Okay. Then there's another thing you can wonder about, which is that, okay, so when Ryu and Kannagi wrote the formula, they didn't write this term, they just wrote this term. But if you just look at this term and this term, it's a very surprising formula. Because this term is a linear function of the state, and this term is a nonlinear function of the state, because it's minus trace of rho log rho. And I mean, that probably just means it's not a formula, right? Like you can't have a nonlinear function of the state be equal to a linear function of the state. So somehow there was some worry that maybe, how does this work, quantum mechanically? No, that's something that bothered people for a while. This one is a nonlinear function also, but you might say, well, if this one is always smaller than that one, then that doesn't help you. So then there was various confusions about that. Okay, then you might also say, okay, so why is this area term here at all? Because it's a duality. So AdS is supposed to be equal to CFT, and I told you there was an isomorphism of Hilbert spaces. And entropy is just something about the states. So maybe you might have thought entropy should just be equal to entropy. Right? Wouldn't that be kind of a simpler formula? Like, why is there this extra term here? Where does that come from? Okay. And then finally, well, generally, so in general, let me remind you that gamma R is not contained in this causal wedge. Okay, and we already saw some examples of that over here. Now, in the previous lecture, when we did bulk reconstruction based on solving operator equations of motion, we argued that only things in the causal wedge were accessible in the boundary. But this seems to violate that, right? Because if I if I have the state in the region R, I can certainly compute its von Neumann entropy. You can't stop me. And now I'm learning something about the area of this surface, even though it's outside of the causal wedge. So if we think, and and some people did think that the causal wedge is the whole story, then this is surprising. So somehow this is telling us either that we shouldn't believe this or that there's more to bulk reconstruction than solving these equations of motion. And so I had various fights with people about this at various points. But anyways, now it's all settled. And so somehow what this suggests maybe, and certainly the nicest resolution of this would be that in fact everything in the entanglement wedge is recoverable here. Right? That would explain this, and then that would also be sort of the nicest thing you could have. I mean, somehow clearly you couldn't go further because at least if we're assuming that the HRT surface is unique, then the entanglement wedges always meet in the middle. And so then if you could go further, then you would have a cloning problem again, right? You would have something that was here and on both sides at the same time. So somehow the entanglement wedge is sort of the nicest answer for this question of what subregion of the bulk is dual to subregion of the boundary. And so the rest of this lecture, I'll try to convince you that that's the right answer. But I'll have to do it using new techniques. I can't do it by solving PDEs. Okay, and so now the idea is that all these sort of features I said of the formula that were a little bit puzzling, I claim that they're all very natural from the point of view of quantum error correction. And so that's now what I'm going to try to convince you.
How would you describe the whole peak page transition? What happens in which part?
Yeah, that's a good question. Let me postpone that till the end. Yeah. You kind of want to know what shows up here and versus here. Yeah, that's right. So let me comment on that at the end. Okay. So any other questions about this? And then now we're going to start talking about so this is all bulk stuff. Now I'm going to talk about how you should think about it from the boundary point of view using quantum error correction. So any more questions about this? Yeah. Yeah. Well, you have to look at the construction. So the way that Douglas did this construction was by sort of sending in shells. And so you're sort of gluing together pieces of the AdS geometry. And the only surface which is extremal is the one that's kind of sitting here in the center, sort of before any of the shells got there. This sort of bifurcate surface is only in this piece.
But it depends which side you're sending the matter in from it.
That's right.
If you send it in only from the right side, the surface is actually at the horizon of the left side.
Yeah, that's right. Yeah. So, but in this example where you kind of try to grow the bridge symmetrically like this, yeah. But yeah, you just look at the geometry and you see where it is. You can actually arrange for them to be different even in Schwarzschild, but it's a little bit more annoying because you have to pick a region which has all of one boundary and some of the other boundary, and then it's kind of hard to draw on the board. So this is kind of easier to draw. Okay. So I'm going to begin by returning to the workhorse, which is the 3Q trait code. So I'm going to talk about RT in the 3Q trait code. Okay, so remember how the 3Q trait code works. So we had our 3 boundary points, 1, 2, and 3. And then we had these causal or entanglement wedges like that. And then we had this point in the center. I didn't draw that very well. Let me. Okay. And then the idea was that the encoded state, psi tilde, had this nice structure where there was this U12, and then we had put in psi on the first Q trait, and then we had this chi on the second Q traits. And remember, this chi was some maximally entangled state, 0, 0, plus 1, 1, plus 2, 2. Now, there's a formula which I didn't write last time, which you can derive immediately from this one, which is the version of this for mixed states. So you can say, what if I have a mixed state that I feed in here? Okay. And then you just do the obvious thing. So the encoded mixed state is U12. Then you have the unencoded mixed state here. Then you take the tensor product with chi on the second 2. And then you put U12 dagger here. Okay, what else could it be, right? Now, here's a state. our goal is to check the Ruta-Kannagi formula. Well, since everything is here is explicit, we can just check by computing both sides of the formula and seeing that they're true. Okay. So let's start by saying that our boundary region is just the third Q-trit down here. So that then, if you like, the HRT surface is here. Well, I want to compute S of rho tilde restricted to 3. Well, so since we're restricting just to the third one, and these U12s are acting only on the first two, we can ignore them, because we're tracing out 1, 2 anyways, and the partial trace is unitarily invariant. So we just need to compute in this state the entropy of the third Q-trit. Now, also the state in 1 is irrelevant, because we traced that out, and so what we're left with is just half of this maximally entangled state of 2 Q-trits. So then its von Neumann entropy will just be log of 3. Because that's the entropy of half of 0, 0 plus 1, 1 plus 2, 2. Okay. Similarly, we can compute S of rho tilde 1, 2. Now, again, the unitaries can be ignored because the von Neumann entropy is invariant under unitary conjugation. So we just have to compute the entropy of this state on the first and second Q-trit. So it's a product state, so we just get a sum of the contribution from here and the contribution from there. So this one is still going to contribute log of 3, because we just have the other half of the maximally entangled state. But now we get a new contribution, which is the entropy of this state that we fed in here. But remember that this status matrix is the same as this state on the code subspace. So this will actually just be the entropy of S of rho tilde. Okay, now I claim this is the RT formula. So let's check it. So in order to check it, I just have to make one definition. The definition is that I define the area operator to be log of 3. And once I did that, I'm set. Because if you look at the third Q-trit, well, there is no bulk entropy because there are no bulk points in here. So that second term in the Ruta-Kannagi formula, that was the bulk entropy, is just gone. And so this is the area. If you look at 1 and 2, well, there's still the area term here. But now there is a degree of freedom in the bulk. And then we have to include the bulk entropy contribution. Okay. So here you see that the RT formula is exactly true in this model, provided you give me the sort of liberty to define the area operator like this.
Why don't you associate a bigger area with it?
Well, because then the formula wouldn't be true, and that would be a pity.
What's the intuition, physiological intuition?
You mean why to call it the area?
Yeah.
Yeah, so let me say in a sec, I think it'll be more plausible. I mean, here again, because it's 3 Q-trits, it's like saying that the thing was a black hole. I mean, it's kind of up to me, to say how I want to interpret things. But I'll claim again that in sort of more general situations, this is the natural interpretation of this. Okay. So first of all, you see immediately, like, there's no issue with the linearity of quantum mechanics or whatever, right? This is just exactly true. So we see that the regime of validity is precisely that this is true in the code subspace. Okay, which is kind of, that's where maybe we thought this should be true. Let me also say that now again, where did this area term come from? Well, now we kind of see, right? It came from cutting this chi. So it came from the degrees of freedom that are sort of fixed within the code subspace, the sort of UV degrees of freedom in the boundary CFT, which, were we to excite these, then we would start getting into these states where there are black holes and so on. So somehow it's the fact that you're restricting to the code subspace. Then you need this area term to come and account for the fundamental degrees of freedom that you left out. Because this thing knows everything, right? This is in the boundary theory. It's unambiguous. Okay. Now, in fact, we can immediately generalize what happened here to this picture I had in terms of quantum circuits. So we remember there we had this R and then this chi. And then we had U R bar. And we had little r bar here. And then that was our encoding up into R and R bar. And now we can do... now I'll make so this chi is some state. Now I can define an area operator to be the von Neumann entropy of chi R2. So that just means the half of chi, which is sitting here, if you remember the notation from yesterday. And then you see immediately that we get a nice Ruta-Kannagi type formula where we get trace of rho LR plus S of rho tilde little r. And similarly, we get S of rho tilde r bar plus equals trace of rho LR plus S of rho tilde little r bar. It's just, again, the same argument. We've got this chi that we fed in that we have to keep track of, and that gives you the area term. Now, to get a bit at what Ofer was complaining about, let's see how it works in the tensor network model. Well, remember, so there, so say this was R, and we had this HRT surface, and then we said that UR was kind of sitting here, and then chi was these states here, and then UR bar was sitting here, and here's R bar. So then when you ask, what is this? So you ask, what is this S of chi R2? Well, it's just a bunch of EPR pairs that are fed here along this line. And so this is just going to be some order 1 number times the length of gamma R, okay, which is the area in 2 + 1 dimensions. And that's sort of the intuition that this thing in general you should think of as scaling like the area. So indeed, the area operator kind of is actually the area operator. Now, there's one rather annoying feature of this formula that's probably some of you are already annoyed about. What's annoying about this formula? What's the area operator? It's a number. That's kind of silly, right? The area operator is not a number, it's an operator. Here the area operator is a C number. So for any code that has this structure, we're going to see that the area operator is a C number. Whereas in gravity, right, it's the area of some surface, and that's built out of the metric, and the metric is dynamical, so you don't think that the area operator should be a C number. So somehow that means that this formalism I was talking about, although it's more general than what we started with, it's still not general enough to allow for what actually happens in AdS CFT, which is that the area operator is non-trivial. Okay. So in the rest of the lecture, so let's see how we're doing. When do I go until? Who's the chair? I go until 1 or 1:30? What? 23. Okay. All right. Okay, that's fine. So I'll see how far I can get. So I now need to once again generalize things to a setting where the area operator can be non-trivial, and then I'll claim that that setting is the one that's sort of basically general enough that that's what we think is actually happening in AdS CFT. Unfortunately, in order to do that, I have to introduce this idea of von Neumann algebras. So von Neumann algebras, they're one of those things where they're sort of there in mathematical physics, but most of us, at least until recently, have managed to avoid them. But it's getting harder to avoid them. A lot of interesting results in the past few years are coming out involving von Neumann algebras. So I don't feel guilty inflicting them on you for the next half hour or so. But I'll save you some pain because I'll only do it in finite dimensions. So if you do it in infinite dimensions, which is where you should really be doing it, then I can't do it in half an hour. Then you need to bring, Barry Simon or somebody here to. You actually do. There's a sense in which it's still they're non-trivial in finite dimensions. Yeah. So I'll explain to. In finite dimensions I can classify them, and I'll do it for you, and we'll see to what extent they're non-trivial.
Sorry. So as you go to the second term, do you see in the larger number that this is maximum order?
Sorry, you mean like this term?
That's what you
Yeah. So that's a little bit subtle, asking which term is bigger. So. Yeah, I was going to comment on that later, but maybe I'll say something about it now. So that kind of depends on how you renormalize things. So the usual story with, let's say, just computing black hole entropy, which is a special case of this, is that you do the Gibbons-Hawking calculation, and you find A over 4G, and you're very happy. And then you compute to the next order in G-Newton perturbation theory, and you find infinity. And then you say, oh, that's interesting, right? And then what you say is, okay, but I forgot that the G that appeared when I did the tree level calculation is the sort of unrenormalized, the bare G Newton. And so if I renormalize G Newton, I can absorb the divergence in the one loop term into a renormalization of G Newton. And then I'm left with a IR G Newton, which is the right thing that should be appearing in the Bekenstein-Hawking formula. So that whole story has an analog here, which has to do with how you think about the code subspace. So basically in the bulk, you have to decide which degrees of freedom you include as part of the bulk. And if you include sort of degrees of freedom up to the Planck scale, then you'll indeed find that this term is large compared to this term, or at least naively, right? I mean, of course, then if you then decide that the bare G is also large, and which it should be, right? Then you can kind of reshuffle things around, and that's how you get out of this issue of which term is bigger than the other one, right? I mean, somehow the right thing to do is to not, to bring the cutoff scale down, to something like the AdS scale, and then you'll be in a situation where this is bigger than that. Okay. All right. So now let me start with the von Neumann algebras. So I know we keep oscillating between fluff and rigor, and now we're back on the rigor side. Okay. So von Neumann algebras. All right, so I'll give a definition. So let H be a complex finite dimensional Hilbert space. I will define L of H to be the set of linear operators on H. So then we say that M, which is a subset of L of H, and might be all of L of H, whoever asked, is a von Neumann algebra. I'll just call it VNA, if several things are true. Well, we need x plus y to be contained in M for all x and y in M. So that's saying it's closed under addition. We need x times y to be in M, again, for all x and y. So it's closed under multiplication. We need that x dagger is contained in M for all x and M. So it's closed under Hermitian conjugation. And finally, we need that any multiple of the identity is contained in M, where this lambda can be any complex number. Okay, so it's an algebra which is closed under addition, multiplication, Hermitian conjugation, and contains all scalar multiples of the identity. Let me just comment that this is not the same as a C-star algebra, in case there are any mathematicians or people who... Someone always complains to me that I should be using C-star algebras instead of von Neumann algebras. It's wrong. I should be using von Neumann algebras. C-star algebras are abstract concepts which live independent of their representation. They can have different representations of the same C-star algebra. A von Neumann algebra is defined by its representation on a Hilbert space, and all the representations are always isomorphic. And that's what physics is, right? Physics, we have the Hilbert space. Okay. Now, given any von Neumann algebra, there are two natural von Neumann algebras, other von Neumann algebras, which it induces on the same Hilbert space. Let me erase this also. And these are called the commutant and the center. So the commutant of M, which is called M prime, is defined as the set of X in L of H such that X prime equals X prime X for all X prime in M. Okay? So it's all the operators on the Hilbert space which commute with everything in the algebra. Just to beat a dead horse, let me again note that for C-star algebras, there's no analog of a commutant. Okay. So that's one, and so you can check homework problem, easy homework problem, check that this is also a von Neumann algebra. Okay, and then the other one is the center, which is written Zm, which is just the intersection of M and M prime. So it's the set of everything which is in the algebra and commutes with everything in the algebra. Okay, that's what how the center is always defined. So let's just do a simple example where we can see all of these three things. So let's take the Hilbert space to be a tensor product, h little r times h little r bar. And then let's take our von Neumann algebra to be the set of all the linear operators just on HR, tensor with the identity on R bar. Yeah, sure. So we can check that that's a von Neumann algebra. Easy. You can also check that the commutant is just the identity on IR, tensor all the operators on HR bar. Okay. Fairly plausible, but maybe another homework problem if you want to check it. And finally, you can check that the center of M is just all the multiples of the identity operator on the whole Hilbert space. Okay. So in this situation, we say that the von Neumann algebra M is a factor. Fairly obvious why it's called that. In fact, any von Neumann algebra where so this is called having a trivial center if the center is just all the multiples of the identity. And in fact, it's a theorem that's hard to prove, although you can find the proof in the appendix of one of my papers. Again, not claiming that I invented the proof, of course not. But anyways, that's a good place to find it. So any von Neumann algebra with a trivial center is a factor. Okay, so anytime you have a von Neumann algebra with trivial center, you can construct this factorization, and then it'll just be all the operators on one factor. And in fact, if you talk to a mathematician, they'll tell you that the definition of a factor is that it has trivial center. And then you'll be sitting here for a while trying to figure out why that's called a factor. And then you have to prove this hard theorem. And then you see that actually it's good to call it a factor. Okay. So let me write that. This is called a factor algebra. Now, not all von Neumann algebras are factors. Otherwise, I wouldn't be talking about it, right? But in fact, the general structure of von Neumann algebras, at least on finite-dimensional Hilbert spaces, is not too different from this. Okay, in infinite dimensions, what I'm about to say would be true for type 1 factors. Okay, and then it's harder to think about type 2 and type 3. But anyways, I'm finite-dimensional. Okay, so here's a theorem. So this is the classification of von Neumann algebras. So let M be a von Neumann algebra on H. So then there exists a decomposition H into a direct sum over some set I'll call alpha, and then within each block of the direct sum there is a tensor product H r little bar alpha such that M is the direct sum of all the operators on each of the first blocks. M prime is the direct sum of the identity on the first factor within each block, tensor all the operators on the second block. And the center is the direct sum of operators which within each block are proportional to the identity but might have different coefficients in the different blocks. And that's the sense in which it's non-trivial. So let me just say clearly. So there's a block decomposition of the Hilbert space, right? A block diagonal decomposition. Well, there's a block by block decomposition where M is block diagonal. in that decomposition. So M doesn't mix between different alpha sectors. Within each alpha sector, there's a tensor factorization, and M is just all the things that you can put there. Any operator you can put on that tensor factorization. So you might say every von Neumann algebra is a direct sum of factor algebras. Okay, and so that's what's true. So for all finite dimensional von Neumann algebras, yes?
We also assume that the all operators of Hilbert space are generated by n and n prime.
All operators are generated by M and M prime.
Because it's not a fully.
No, that's not true. No, there are operators that are not generated by M and M prime because both M and M prime are block diagonal. So any operator that mixes between the blocks is not generated by M and M prime. That's the whole point. So in a factor, the whole thing is generated by M and M prime, but in a general operator algebra with non-trivial center, it won't be true. And indeed, you can think of this alpha if you like. This alpha is sort of labeling the eigenvalues of the center. It's kind of, it's just each this set of alphas is in one-to-one correspondence with the, Yeah, because the center is just you get it by just varying these lambda alphas. Okay. All right. So that's kind of all you need to know about von Neumann algebras for the there's a basic structure of von Neumann algebras for what I'm going to say. Okay, now we can get rid of this. So there's one other property of von Neumann algebras that I need, though, which is that there's an entropy which you can define for them. So you probably learned, as undergraduates or whatever, that entropy of a subsystem is something that you associate with tensor factors, right? So if I have a Hilbert space which is HA times HB, then I can have a state rho AB, and I take the partial trace onto A. And then I can compute minus trace of rho A log rho A. Okay. Now I want to, in this language, interpret that as saying that that's the von Neumann entropy of the state rho AB on the subalgebra, which is all the operators on the tensor factor HA. So then the idea is that I want to define an entropy of a state on a subalgebra instead of a subfactor. And when this M is a factor, then it's just the usual thing. So if M is a factor, then it's just minus trace of rho R log rho R. But then I want to now say that, well, it's true that there is a definition of von Neumann entropy for any von Neumann algebra M. And I'm now going to tell you what it is. And I'm going to need that to write the correct version of the Kannagi formula. Okay, so here's the idea. So let rho be any state on H. I can look at rho with respect to this block diagonal decomposition, which the von Neumann entropy or von Neumann algebra promises me. And what will it look like? Well, and I'm only going to be concerned with the diagonal blocks. So up here, I'll have something that I call P1 rho R1 bar. And on the next block, I'll have something I call P2 rho R2 bar, and I just keep going. And then the idea is that, so I choose these coefficients P so that what I get here is something with trace 1. So if you just first don't try to decompose and you just ask, what is the property of this matrix here? Well, it's still going to be Hermitian and positive because the whole matrix is. And so if I want to interpret it as a state, the only issue is that its trace will be less than or equal to 1. Okay? But I can just sneak in a positive coefficient here, and then now I have something whose trace is equal to 1. So I just do that going down all the blocks. Now I can define the entropy. So then the idea is that the entropy of rho on a general von Neumann algebra has two terms. The first term is a kind of classical piece that comes from these coefficients P alpha. So maybe it's not obvious, but these P alphas clearly have to add up to 1 because that's the whole trace has to be 1, right? And they will be positive, well, non-negative. So there will be some von Neumann entropy that comes just from knowing which block you're in, not being sure which block you're in. Right? And then there will be an additional contribution where I average over the blocks P alpha, and then within each block, I compute the von Neumann entropy, the usual von Neumann entropy, just on S rho R alpha. Okay, so this guy here, then I can take the partial trace over the factor within this block, and get a von Neumann entropy, which I put here. Okay. Now there's some abstract way of trying to motivate this without going to this block decomposition and so on, and arguing that if you want something that obeys the property of entropy, it has to be this. Okay, fine. But anyways, this is the definition. And this does obey appropriate generalizations of all the things you want entropy to obey, being convex and 0 on pure states and so on. Okay. I should also mention, yeah, sure. So there is a algebraic version also of relative entropy. So I guess also no one has mentioned relative entropy in this. So let me just say briefly. So maybe I'll put it up here. So relative entropy is defined between two states, rho and sigma. Okay, and there's a 50% chance I'll get the sign wrong here, but just bear with me. So it's trace of rho log rho minus trace of rho log sigma. Okay. So this is something you can define for any two states. It has a nice interpretation as a measure of distinguishability of the two states. So you can show that this is positive. That's a fun homework problem. Then you can show that it's 0 if and only if the states are the same. Okay. And so this is if you go talk to the real people, they never talk about von Neumann entropy. This is what they talk about. This is kind of really the fundamental thing that everything else comes from when you talk about entropies. So this is something you can define. So if you have a subfactor, if you have a factor algebra, you can define this, for the reduced density matrices. In fact, there's also an algebraic definition of this. So this is like maybe I should put R's here, so I can take a partial trace and do that. But then there's actually also an algebraic definition of relative entropy, rho sigma m, which makes sense for arbitrary algebras. And it's some formula like this, but maybe I'll just say it in words. So basically, you compute the relative entropy of these p alphas, and then you average over the p alphas the relative entropy of the states. Okay, so it's the same thing. Now let me comment that since I don't know if any of you watched Edward's lectures last summer, there's another definition of relative entropy in terms of the relative modular operator. That's kind of the more fundamentally algebraic way of thinking about it. The thing I just said is equal to that. And in fact, in finite dimensions, it's better because the relative modular operator definition has various annoying features in finite dimensions. So you kind of only can really define it by doing some analytic continuation. But this definition is always correct. Okay, so let's see. Now what time is it? 57. Okay, so now I think it's a good time to stop. So I've introduced all this machinery. You're given a von Neumann algebra. You can define its entropy of a state on a von Neumann algebra, and you can define the relative entropy of a state on a von Neumann algebra. And so tomorrow I'll explain how to use this to understand the Ruta-Kannagi formula, and then see if we have any time left over for symmetries. Okay, thank you.
Questions?
Yeah.
So I was just wondering about the equivalence between the more mathematical definition of von Neumann algebras and what you gave here. If I recall correctly from Weekend's 1803 notes, that von Neumann algebra is defined as a weak limit of a C-star algebra, and so that has both bounded operator and also by definition has weak limit. I can't immediately see how that can be equated with the definition.
I mean, I'm finite dimensional, so you don't have to worry about. Yeah. So the key thing about being finite dimensional is you don't have to worry about these topological closure properties. Yeah. And operator topology is really you don't do that unless you have to do it. I had to do it recently, so I know. So you don't have to worry about any of those, and then it's the same. So there are various equivalent definitions of von Neumann algebras. Some of them are designed to try and make it look abstract. like C-star algebras, but then they always have to introduce this thing they call the pre-dual, which is kind of sneaking the Hilbert space back in. So, I'm a physicist. I mean, for the same reason that we were discussing, I don't like category theory. If there's a thing I can talk about, I want to talk about the thing. I don't want to abstract the thing away and then get contorted. Yeah.
Okay, let's something.
Yeah.